I'm Maria Lombardi, and I'm a postdoc at Italian Institute of Technology. This talk is about nonverbal leadership emergence in working groups, and this was done when I was at the University of Bristol. I'll start with a brief introduction about nonverbal leadership emergence and what's our research question that we want to address. Then I'll move on the experiment that we performed to answer that question with the related data analysis, and then the conclusion. So as you well know, in interesting phenomena can emerge from the collective behavior of a group of interactive agents that cannot we explain in terms of the single agent dynamics. Probably the most famous collective behavior is the coordination and the synchronization within a group, but the coordination is also a key element for another interesting collective phenomenon, that is the leadership. Many examples of leadership exist both in animal and in human world, such as a flock of birds during the migration, the conductor's role in an orchestra, or in some group scenario. Specifically, we are interested in nonverbal leadership emergence in working groups. With the nonverbal leadership, we mean that the leader is able to influence the other members of the group by means of nonverbal cues. For example, by moving first or with some strong personal traits. What's our research question? Basically, we are trying to find a mathematical method to identify the leader in a coordinated working group when the leader is not designated a priori. And to answer this question, we need to define who we characterize as leader. In this work, we define the leader as the individual whose locomotion behavior influences the others the most. For example, in this picture, we have that at time t, the red man is moving upwards, while the black man is moving towards the top left corner. We say, according to our definition, that at the red man is the leader if at the time t plus a certain delay, the black man adjusts his heading direction according to that of the leader. In general, understanding the mechanism underlying the leadership emergence in human group can be useful for many applications. We have, for example, that during an evacuation in an emergency situation, if the leader has a global knowledge of the building, she can be able to guide the others towards the exit. Or we can analyze also the pedestrian flows in a shopping center, identifying leader-follower patterns or cluster formation, or finding and disconnecting the leaders from the crowd. We can also prevent that violent behavior of a small group can spread among the crowd. So to answer our research question, we performed some experiment at the Brown University, and two groups of four people were involved. Specifically, each participant was placed in one of the or vertices of a square configuration. The position were front left, front right, back left, and back right, and the interpersonal distance was either 1, 2, or 4 meters. They were instructed to walk across the room and to change direction or speed twice at self-selected times, and furthermore, they were explicitly instructed to try to stay together with their neighbors. We can have two different types of trials. In change direction trial, we have a sequence of left-right commands. In the change speed trial, we have a sequence of slow-fast commands. Participants shuffled their position at the beginning of each trial. This is a video of the experiment that refers to a 10 participant experiment, but it's just to show how we performed our experiment, because the equipment and the instruction are equal to our case with only 4 participants. So how we can identify the leader in a coordinated working group? We start from an experimental trial. It can be either a speed change trial or a direction change trial. So we can have either a leader in heading direction or a leader in speed. In the first case, we proposed the time-dependent delay directional correlation that basically assess the difference in heading direction at each time between each pair of pedestrians. In the second case, we proposed the time-dependent delay speed correlation that basically assesses the difference in speed at each time between each pair of pedestrians. With these two metrics, we can identify who is the leader at each time instant of the trial. Summing the percentage of time in which a specific pedestrian is identified as a leader, we can evaluate the individual leadership index. Here I'm going to explain a bit of math. This is the formula that we can use to evaluate the time-dependent directional correlation. Basically, these metrics compare the heading of the agent I at time t with the heading of the agent j at time t plus a certain delay tau. It is basically, I can move this one, yes. This is basically based on the scalar product between the velocity vector of the agent I at time t and the velocity vector of the agent j at time t plus tau. If the scalar product is 1, this means that the two heading directions are parallel, and this means that the agent j after a certain delay has adjusted his heading direction to that of the agent I. If the scalar product is 0, this means that the two agents are going to a completely different direction. This quantity is then averaged over a symmetric time window. So following this the definition, we can say that the pedestrian I leads the pedestrian j at time t if the value of delay tau that maximizes the value of correlation c is positive. Here we have just an example of a change direction trial where the sequence of commands was turn left and then turn right. We can build for each pair of pedestrian, we can build basically the heat map showing the values of correlation. And we have on the x-axis the duration of the trial, while on the y-axis we have different values of delay tau. In green, we have the values of tau that maximize the correlation C for each time instant. As we said before, we can basically sum the amount of time in which a specific pedestrian is identified as a leader, and we can build this bar plot that basically shows the level of leadership taken by a specific pedestrian during the trial. In this specific case, we have that the pedestrian in the front right position takes the leadership for around 90% of the trial. The knowledge of the values of tau allow us also to reconstruct the network of interaction between the participants. Here we have that each node of this graph is a pedestrian, and the arrow connecting two different nodes represent the direction and the strength of the influence that a pedestrian has on the another one. We can reconstruct this network for a small window of time, so we can basically see how the either follower patterns change over the trial. Very similar, we can define the time-dependent speed correlation. Here we have that we compare the speed of the agent A at time t with the speed of the agent J at the time t plus 2. Here we evaluated the difference in module between the velocity vector of the agent I, always at time t, and the agent J, always at time t plus 2. If this difference is 0, this means that the speeds are equal. This quantity is then averaged over a symmetric time window. Following this definition, we can say that the pedestrian I leads the pedestrian J at time t if the value of delay tau minimizing the value of correlation C is positive. The difference with the previous case is that here we aim at minimizing the value of correlation. We applied our method to the data that we collected from the experiment, and we were able to detect different type of leadership emerging from a working group. The first type of leadership is that one depending on local visual couplings. The second one is the individual leadership that is more related to a participant characteristic locomotion behavior that can be so strong to dominate all the other. Here we have the bar plot showing the level of a percentage the level of leadership taken by each pedestrian grouped by position, both for the group 1 and the group 2. We performed a three-way mixed ANOVA with two different conditions, the change in direction and the change in speed for 4 position and 3 interpersonal distance. As we expected, the leadership was taken prevalently by one of the two pedestrians that were in one of the two front position. In fact, from the analysis, we see that the position in effect was statistically significant, and the front position are statistically different from the back position. The evidence of the individual leadership is more interesting because we noticed that the pedestrian 4 in the group 2 basically takes the leadership independent of his position in the group. Here we have that the participant 4 basically takes the leadership also if it is she is in the back left or in the back right position. And this is the level of the leadership of the player 4 is statistically different respect to the others. To conclude, basically, we propose a mathematical method to identify the leader in speed and in heading direction in working group when leader and follower role are not designated a priori. I would like to underline that this study is not to discover any type of leadership or understand something particular in the experiment, but this study is to basically try to formalize mathematically basically the mechanism of the leadership. In fact, with this method, we can get information about the leader-follower patterns within a group, reconstructed the network of interaction, and we can also have information about how these patterns change over trial, over time, because we know that the leader can be time dependent, so the leader can change. And of course, this proposed method needs to be tested with more extensive data and can be generalized to a larger pedestrian group. In fact, we are currently working to extend this methodology to swarm scenarios. I would like to thank my co-worker, Mario, William, and Greg, the lab crew, and all people who took part in the experiment. And thank you all for your listening. I hope to be in time.
You were more than in time. You were the best in time. You are a leader in timekeeping. No, that was fantastic, Maria.
Always worried to be in time during the talk.
Well, you were perfect. You were unbelievably punctual, and I do love that so very, very much. Most people won't know that I've been stalking Maria for at least 2 years now, because as you will all have seen, her work is incredible and incredibly thorough, and I think has been the perfect way to prepare us for our workshop this afternoon on ways to quantify coordination. So I need to thank you for setting the tone for that, because it really is really quite wonderful what you've put together there. And I'm hoping that people like myself will continue to bombard you to try and use some of your tools in some other data sets. As a nice bridge from our previous talk on spontaneous herding, you obviously are talking about another spontaneous or emergent property of leadership. So I think you should definitely be talking to some of the people working on herding literature, trying to form a bridge there. But I have some various questions. One is a more conceptual one, which you don't have to answer, but which I'd like to throw out there, which is, what is a leader? And you've looked at least 2 different ways people can lead. They can lead by changing direction, or they can change in a more subtle way, simply by changing their speed. It's a more of a nudge than we're going this way. So I think that one thing that your work highlights is that there are different kinds of leaders. And Peter Keller talked about that as well earlier today. He said, you know, there can be leadership by default in a dyad. If nobody takes control of that dyad, you end up going incredibly slowly and you never reach your goal. So we in our experiment had, you know, a leader by default, and then subsequent work that Peter and his group have done have looked at people who take the lead, who are active leaders. And I think that in here you have sort of somewhere in between, because you still gave them instructions, and there was somebody in the group to take the lead, as it were, but based on some instructions. So I think that there's something nice there to think about. Questions that I have for you specifically is that I thought it was quite interesting that you tried to look at the dynamic time course a bit more. So where you looked at what I think is sort of like this transition into the leadership roles, where you try and quantify the coupling between individual nodes across time. And I think that that's really where I think all of our work needs to go. It's less interesting from a signal point of view to be in one state or another. Obviously, it's interesting if you then correlate it with other, you know, more behavioral, psychophysical things. But from a pure maths point of view, it's what's in that signal when you transition right into that leadership role. So I thought that was really interesting. I don't know if you have anything more to say about how we can dig into the data in a more dynamic way, like you've proposed.
Yeah, basically to reconstruct the network of interaction, basically the links, you know that the links basically that can change over time, because the leadership and the influence between that a pedestrian has on another basically is a time variant. So the network that we can reconstruct needs to be time variant itself. Basically, the link basically is constructed on the value of tau that we evaluated with our metrics. Basically, the exact mechanism that basically change these links. I don't know which is the exact mechanism that changes these links, but I can observe experimentally that the leadership is a time variant phenomenon. I collaborate with Professor William Warren, that is a psychologist and a more cognitive science and me. My work is to try to mathematize some phenomenon that we can see in the nature. It can be quite complicated because the nature and the human brain is so complicated. So we need some way to simplify all of the mechanisms that can happen in a human brain.
But I think that that's exactly what you've done. And I think that the tools that you've been using are going to be incredibly useful going forward. So I really will hope that people will reach out to you. I know I have already, because I think that there is a lot to be said for using these kinds of mathematical tools to better dive into these dynamic time course data sets that we have. One last question I have for you is, again, related to some of the work I'll be presenting after the lunch, and that's a little ad, to please come back and join us at 1:30 for the second afternoon session of this day 2 of Social Bridges. We're going to be talking again about group walking. But in the two studies I'm going to present to you, on the one hand, we don't have movement in one of the study designs that we have. And I think that there might be something interesting to think about in terms of when there's no transverse movement at all. So there can be only temporal information, but without spatial changes. And then the other, where so in the first one, the configuration is that everybody's looking forward, much like in your case. But in the other, we have people standing in a circle. So rather than having this front-back bias, which we see in your data and in Alan and Mark's data from yesterday, all members of the nodes have access to, can look at, can visually couple to one another. So I think it'd be very interesting if we could use some of your analysis tools to look at that kind of data to see if there's something interesting there.
I think that this method can be easily generalized to also other kind of tasks or of configuration, because we are trying to apply it also to the mirror game task, that is the task that also Peter showed before. And basically we need just to transform the variable from an XY space to an angular space. So for example, in the mirror game task, we have not a leader in X, Y coordinate, but just a phase leader where we evaluate the angle theta, for example, between the oscillation of two or more players in the task. So I think that this method can be generalized to other tasks. The important things that should be some kind of movements in the task.
Well, we just need to find you some times that you can. I will get you one of these days.
Okay.
But on that note, I'm going to thank you, Maria, for your time and for your incredibly wonderful talk. You've got some compliments coming up in the stream. Nobody has questions because it was so perfectly presented, so clear, even though it was full of maths. So it just goes to show either we have a very biased crowd this morning who are mathematically oriented.
Tried to limit the math in this slide.
You didn't. You gave us just the right amount, so you got us all thinking. It was perfect. Thank you so very much, and I hope that you are well and safe in Italy, and that we will have a chance to meet in person very soon when all this nonsense dies away.